Hello students, good morning all of you. Today we are going to learn another new topic students in the unit gaseous state. Okay, so last week we have completed Andrews isotherms of carbon dioxide and also critical constants, right? Hope you all understood that topic. Fine. So today we are going to learn a new topic students, that is relationship between critical constants and Vanderwaal constants, which is also a very important question. Take a fresh new page or continue in that page if you have some blank space students after the last topic, that is relationship between critical constants and Vanderwaal constants. Critical constants means TC, PC and VC, and whereas Vanderwaal constants means small letters A and B. Okay, so put the side heading and kindly underline students. So students, first I want to ask you a question. What is Vanderwaal's equation of state for 1 mole of a gas, students? Do you remember? P plus A by V square into V minus V equals to RT, right? That is Vanderwaal's equation of state. So immediately after the side heading, relationship between critical constants and Vanderwaal constants, you write down Vanderwaal's equation of state for 1 mole of a gas is P plus A by V square into V minus B is equal to RT. Okay, a well-known reaction. Fine, equation. So below what I did was, students, I removed the brackets. So P plus A by V square into V minus B. So open the brackets, multiply the terms, both the terms, students. So what do we get? P into V, PV. Okay, P into minus B, minus PB. Plus A by V square into V, A by V, minus A by V square into minus B is minus AB by V square equals to RT. Understood that? Multiply both these terms, remove the brackets. Fine. Now, so in the brackets, what you are supposed to write? Multiply the equation both the sides by V square. What is it, students? We should multiply both the sides of this equation with the V square. Right in the brackets, multiply the equation both sides by V square. Okay, so each term should be multiplied by V square. Ready, students? PV into V square, PV cube, minus PB into V square, PBV square, plus A by V into V square. V gets cancelled. What remains? AB minus AB by V square into V square. So AB is equal to RT into V square, RT V square. Got it, students? Fine. Next step what I did, this RT V square which is there on the right side, I moved it to left side of the equation. So when it comes to left side, it becomes negative. Why? Because right side it is having a positive sign. Okay. So PV cube minus PBV square. This is minus PBV square. Now when this RTV square comes to left side, minus RTV square plus AB minus AB minus AB. So there is nothing right side, so we should write equals to 0. Okay, so next step, students, look at carefully. This term is PBV square, this term is RTV square. What is common in both the terms? V square. So we can take V square common out, and therefore next step will be PV cube minus. So V square, if I take common out, what remains inside the brackets, students? PB plus RT. So here there is minus, no? Okay. So minus into plus is minus, right? So you cannot write minus is there, now here also minus. So you should be very careful. So plus RT plus AB minus AB is equal to 0. Okay. Now in the brackets, write down, divide this equation by P. Divide this equation. This equation means what? This equation by capital P. Okay. So what do we get, students? PV cube by P minus V square into PB plus RT by P plus AB by P minus AB by P is equal to 0. Okay. So if we divide with P, what happens, students? Next step, try to write down in your notebook what comes next. So next step, V cube minus V square into B plus RT by P plus AB by P minus AB by P equals to 0. Okay. So after dividing with P, we get the final step as V cube minus V square into B plus RT by P plus AB by P minus AB by P is equal to 0. Okay. Mark this as equation number 1, students. Okay. Next, below write down. Students, look here. This equation is beginning with V cube. Hence, this equation is called as a third degree equation in volume. So, this is mathematical language. Third degree equation in volume. What's the meaning of it? Volume has 3 values. It might be 3 real values or 1 real and 2 imaginary values for a given value of pressure at a particular temperature. Okay. So below the equation, write down, students. This is called as third degree equation for in volume. That is, it has 3 real roots or 1 real and 2 imaginary values for a given pressure at a given temperature. Okay. Right, students. So what is this volume having 3 values? Okay. Just turn back your pages, students. Last week's class, go back and look at the diagram of Andrews isotherms of carbon dioxide. Okay. So when you observe that diagram, I have just drawn a rough figure here, students. Don't draw it in your notebooks. Just look at that diagram. So x-axis, what is taken by Andrew? Volume, and y-axis, what is taken? Pressure is taken. Okay, so this is the graph we could get, and these are the isotherms. Fine, students. First isotherm at 13.1 we have learned, and Andrew named it as ABCD. Okay, so if you observe that isotherm, students, it was studied at 13.1 degrees centigrade corresponding to some pressure here. Okay. So at that temperature, for a particular pressure, there will be, look here, I am writing again A, B, C. Fine. So there is a volume value at B and there is a volume value corresponding to C. How many values are there? Only 2 values were there, students. Okay. So when Andrew has done the experiment on carbon dioxide, he could find that there are 2 values of volume at one temperature at a particular pressure. But this equation tells us that volume should have 3 values. Okay? Then where is the third value? Third value is missing. So now Vanderwaal is sitting like this. Okay? He couldn't find the third value of volume. But there was a friend like me who is very much loyal and helpful to Vanderwaal. And his name is Thomson. Okay? So Thomson helped Vanderwaal students. So what did he do? He has taken equation number 1. Okay, so what is R in this equation? Gas constant. It has different values having different units, and so he substituted R value and he has substituted A and B, which are nothing but Vanderwaal constants, and using these values, what he did, students, at different pressures, at different constant temperatures, what he did, he calculated the volume of the gas. Okay. So this is all he is doing on a paper. Just he is trying it theoretically. Okay. Andrew has done it experimentally. But here Thomson, what is he doing, students? He has taken equation number 1 derived by Vanderwaal, and what is he doing? He substituted the values of capital R, small letters A and B, and he was measuring the volume, changing the pressure values at various constant temperatures. Okay. Now in his pocket he has a set of data. So any scientist, when he is doing the experiments, or theoretically when he is doing some calculations using his brain, what he does, he will definitely use a paper and a pen, and immediately he will plot the graph. The same thing Thomson also has done with the set of values of volume, pressure and temperature, students. Okay. So the isotherms are obtained by plotting a graph between pressure and volume using the values obtained from Thomson's theoretical observations and calculations. He could help Vanderwaal in finding this third value of volume at the same temperature, at the same pressure. Are you ready to look at the isotherm, students? Okay. Take a paper, take a pencil and scale, and be ready, students. So students, draw the graphical representation of the isotherms obtained from Thomson's values. So you can write about the graph. Thomson substituted the values of capital R, small letters A and B in equation 1 and calculated the values of volume at different pressures at different constant temperatures. Later, he plotted a graph between pressure and volume, and various isotherms are obtained as follows. So below you can draw this graph, students. Take a pencil, scale. So on x-axis volume is taken, y-axis pressure is taken. Carefully draw the isotherm, students. The same temperatures what Andrew has taken, 13.1, 21.5, 31.1. Okay. The first isotherm ABCD. It's just looking like Andrew's isotherms, na, students. Draw it carefully, ma. And if you notice the difference between Andrew's isotherms and these isotherms, can you notice the difference, students, between the two isotherms? They are called as experimental isotherms. These are called as theoretical isotherms. Same, everything is same, na, students. Boundary is there. Okay. Horizontal portion is there where liquefaction takes place, but there see the isotherms here. There you can find horizontal isotherms, and here the horizontal portion is replaced by curved portions, students. Okay. So why I have marked these horizontal lines? To show the value of volume, the third value shown by Thomson. Okay. So the horizontal portion where liquefaction takes place is replaced by curved portions in these theoretical isotherm, students. Okay. So have we come and students, see, mark this point as L, this point as M, and here this point as N. Okay. The name of isotherm is ABCD only, But extra points you write down now. L, here M and N. Okay, and also mark a dotted line here and one more dotted line here. Okay, C, one dotted line at B, one dotted line at M, one dotted line at C. Have we completed the diagram? Okay, now we will learn about these isotherms, students. So students, as I told you, the horizontal portions of experimental isotherms means what? Andrews isotherms of carbon dioxide are replaced by curved portions and curved portions in the isotherms shown by Thomson. Okay students, and for example students, look at the isotherm 13.1. Here the name of the curved portion is BLMNC, which shows us that there are three values. One value at point B, second value at point M, third value at point C. Okay, so which is in accordance with equation number 1 derived by Vanderwaal. Okay, so if you can write the points, students, I have written here. Please make it fast and copy it down fast. Okay, reading out for you, students. Horizontal portions of experimental isotherms are replaced by curved portions in theoretical isotherms. Students, if you can underline, please underline horizontal portions of experimental isotherms and curved portions of theoretical isotherms. Okay, so next you can write, for example, the isotherm at 13.1 degrees centigrade tells us that the curved portion named BLMNC shows that there are how many values, students? 3 values for volume at 1 pressure and at 1 temperature, which is in accordance with Vanderwaal's equation number 1. If you can write down, please write it down in your notebook, students. Don't waste time. Don't look here and there. Okay, I will erase this point now. So students, next point, what do we understand from these isotherms? So as we have learned from Andrews isotherms, students, as the temperature increases above 21.5 degrees centigrade, what happened to the horizontal portion, ma? There it has become shorter and finally at 31.1 degrees centigrade it has become 1 point. There we have learned that there is no distinction between gaseous and liquid states of the gas. Okay, so here also if you observe, as the temperature increases, what is happening? The curved portion is becoming smaller and smaller. So what do we understand from this curved portion becoming smaller and smaller with the increase in temperature? See, look here, students, we have seen that the curved portion implies that there are 3 values for volume at 1 pressure corresponding to 1 temperature. So when the temperature is being increased, the 3 values of volume, they are coming closer and finally at point F, that is at 31.1 degrees centigrade, all the 3 values, they have merged into 1 value. That means we can say that they are all, or they have become identical at 31.1 degrees centigrade. That means below critical temperature, there are 3 values for volume at 1 pressure corresponding to 1 temperature, but at critical temperature, what happens, students? All the 3 values have become identical. Okay, so write down the same point, students. As the temperature increases, curved portion becomes smaller and smaller. That is, the 3 values of volume come closer and closer and finally become identical at point F, that is at 31.1 degrees centigrade. So below this write down students. Therefore, below critical temperature, you all know that 31.1 is called as critical temperature. That is at point F. Okay. So at below critical temperature, there are three values for volume. There are three values for volume for one pressure at a particular temperature. Full stop. But at critical temperature, all the three values of volume have become identical. Okay, so if you understood these points, now we can continue the further derivation of relationship between critical constants and Vanderwaal constants. So below that, write down at critical temperature, V is equal to Vc. Okay. So as all the three values have become identical, we can take the value of volume as Vc at critical temperature. Okay students? Therefore at critical temperature V is equal to Vc. If we bring this Vc to left side, what happens? V minus Vc. Then what remains right side students is equal to 0. Write on the next step. V minus Vc is equal to 0. Next. Cubing this equation, we get that means multiplying 3 times, we get V minus Vc whole cube is equal to 0. V minus Vc whole cube, it's in the form of A minus B whole cube, which is equal to students. Do you remember? This is a 10th class mathematical equation. A minus B whole cube is equal to, write down A cube. Write it in the column students. A cube minus 3a square b plus 3ab square minus b cube. Okay. Same you apply to V minus Vc whole cube. So what do we get ma? V cube minus 3v square Vc plus 3v Vc square minus Vc cube is equal to 0. Now mark this equation as equation number 2. Okay, next. Below that, write down students. So we all know that at critical conditions, the temperature will be equal to critical temperature, pressure will be equal to critical pressure. Fine. So write the same here students. At critical condition, T is equal to Tc, P is equal to Pc. Okay. Next, substituting these values. What these values means what? T is equal to Tc and P is equal to Pc in equation 1. Turn back your pages and look at equation number 1 students. Okay. So in that equation, we will substitute Tc in the place of T and Pc in the place of P. Okay. So after substituting, the equation 1 becomes V cube minus V square into B plus R Tc by Pc plus AB by Pc minus AB by Pc is equal to 0. Mark this equation as equation number 3. Mark this equation as equation number 3. Now, if we combine or if we try to compare equations number 2 and 3, what do we get? The next step from equations 1 and 2. Write down from equations 1 and 2. From equations 1 and 2. Sorry students, it is from equations 2 and 3, not 1 and 2. Okay. In equation 1, we have substituted Tc and Pc, right? So now look at the equations 2 and 3. Okay. So please below that write down at the critical point, equations 2 and 3 must be identical. Why? Because students, now we are concentrating at critical conditions. V is equal to Vc, T is equal to Tc and P is equal to Pc. Fine. So at critical conditions, equations 2 and 3 must be identical. So what happens? The coefficients of similar powers of V must be equal in both the equations. You did not understand this sentence, right? So that's why I have written once more equations 2 and 3. You don't write in your notebook. Okay? Look here students, equation 2. V square minus 3V square VC. The coefficients of similar powers of V must be equal. Look here. In this equation, there is V square. In this equation, there is V square. Second term. Okay. Coefficient of similar powers of V. V square coefficient 3VC. V square coefficient B plus RTC by PC. That means they should be made equal. See here. 3VC. 3VC equals to B plus RTC by PC. Okay. So write down 3VC is equal to B plus RTC by PC. Mark this as equation A students. Don't use 1 again. That is over. Na? So these are same. Na? So they are already equal. Okay. We need not write them once again. Next coming to third term. Look here. There is V here. There is V here. So coefficients of similar powers of V. So what is the coefficient of V? 3VC square. 3VC square. Look here. 3VC square should be equal to coefficient of V here. A by PC. A by PC. Now it is clear? Right. Mark this as equation B. Next, anyhow, first term we made equal, second term we made equal, third term made equal. So finally, the fourth term, even if there is no similar coefficients, no coefficients of the similar powers, we can make them equal. So finally, third one is VC cube is equal to AB by PC. Mark this as equation C. So next students, below write down dividing equation C by equation B. Dividing C by B. Okay. So what do we get by dividing like that? VC cube by 3VC square is equal to AB by PC by A by PC. That is VC by 3VC square is equal to AB by PC into PC by A. Okay. So VC cube below in the denominator there is VC square. Okay. So VC square gets cancelled. 1 VC remains in the numerator. Right hand side A gets cancelled. PC gets cancelled. Okay. What remains? VC by 3 is equal to B. Therefore, VC is equal to 3. Okay. Relationship between critical constants and Vanderwaal constants we are doing students. VC is equal to 3B. Okay. Below. Substituting value of VC in equation B. Substituting value of VC in equation B. So what do we get? 3 into 3B whole square is equal to A by PC. 3B whole square means what students? 9B square. So 3 into 9B square is equal to A by PC. 3 into 9 how much? 27B square is equal to A by PC. So therefore PC will be equals to A by 27B square. Okay students, VC we got it as 3B, PC we got it as A by 27B square. So students, now we have the values of VC and PC, right? So these two values, if we substitute in equation A, what do we get? So write down below that. Substituting the values of PC and VC in equation A, we get, substituting the values of PC and VC in equation A, we get 3 into 3B is equal to B plus RTC by A by 27B square. Okay. We substituted the value of VC and PC students. Fine. So now we will elaborate this equation. 3 into 3b how much? 9b is equal to b plus RTC into, students, RTC by a by 27b square. So this 27b square comes up. Okay. So RTC into 27b square by a. Now bringing b from right side to left side. Right side what is there? B plus. Okay. If it comes left side, what happens? Minus b. So 9b minus b is equal to, what remains right side? RTC into 27b square by a. Next below, 9b minus b, 8b is equal to RTC into 27b square by a. Okay. Now cross multiplication, students. RTC into 27b square is equal to 8b into a, 8ab. Next, RTC is equal to 8ab by 27b square. So numerator there is b, denominator there is b square. So b gets cancelled. So what remains? RTC is equal to 8a by 27b. Therefore, TC is equal to 8a by 27rb. So okay students, VC value, PC value and TC value, we got it as 8a by 27rb. Now we will combine all these values and see what we get. So students, relationship between final conclusion, relationship between critical constants and Vanderwaal constants is given by, write down, the relationship between critical constants and Vanderwaal constants is given by PC VC by TC is equal to PC VC by TC is equal to, okay. So write down the value of PC, a by 27b square into, what is the value of VC? 3b by TC. TC value is 8a by 27rb. Okay students. So PC VC by TC is equal to a by 27b square into 3b into, now 27rb comes up by 8a. Now start or try to cancel the common terms, students, numerator and denominator. A, next B, 27, 27. Okay. So what's remaining? PC, VC by TC is equal to 3R by 8. Okay. So this is how we derive the relationship between critical constants and Vanderwaal constants. So enjoyed the derivation, students. Please don't keep the notebook aside. Try to practice this derivation, which is very, very important. I don't say that you will get the question. Derive the relationship between critical constants and Vanderwaal constants. But this question can be split into 2-3 parts and you can be asked in various ways. Okay. So try to learn this question as this is also one of the important questions, students. Okay. So meet you in the next class with a new topic, students. Take care, stay safe and bye-bye.